our statement is every subgroup of a cyclic group is cyclic. So first we check what is given and then what we have to prove. So here the given thing is a group is cyclic and then we have to prove its subgroup is also cyclic. So the given part given is let G be a cyclic group. And the second thing, and let H be a subgroup of G. Then what we have to show? We have to show H is cyclic. This we have to show. Now what is the meaning G be cyclic? That means G is cyclic mean G has some generator, or by definition of cyclic G is something like this. Either we can say A or we can say A raised to power n. That means all elements are expressible in terms of some power of A of G, and n belong to Z. That means n is integer. That means A can be 0, n can be 0, n can be 1, or in expanded form we can write like this: A minus 2, A minus 1, A0, A1, A2, and so on. This is infinite. This is the group of infinite order. It can be finite, but it is not specified that it is finite or infinite. So we are taking like this. And H is subgroup. So one thing, either this element means it is equal to identity. The zero power of any element is identity. If H is equal to E, then obviously it is cyclic group. Then obviously H is cyclic. So what we let H is not E. So the result is proved, and nothing to prove. So let H is not equal to identity set. Therefore, there exists some element in G which will belong to H, because H is subgroup. Then some element of G belongs to H. That is let AT belong to H. positive, for T positive. That means we are taking some element T positive. There is no problem, we can take negative also. If T is negative, then what happen? If T is negative, then minus T is positive, and then we can say, then we can take A minus T belong to H. That means in both cases we can say that some element of G is in H. Now, if these type of elements are in H, then we suppose there is some least number, least positive integer such that AM belong to H. That means now suppose AM belong to H, where M is least positive integer. M is the least positive integer. We claim H is equal to AM. H is equal to AM. This mean you can say in expanded form, this is AM raised to N and N belong to Z. I give some example here. Some example we can say, if I take G is suppose 2 minus 2, 2 minus 1, 2 0, 2 1, 2 2, so on. This is a group. Now, if I take the here generator is 2 of G. Now, if I take H is equal to 2 raised to 2, that means I take this element. Now, we check whether this is group or not, subgroup or not. That means this we can say 2 raised to 2 raised to N and N belong to Z. Mean what? If I expand it, this number become 4, and what I get? I get element 4 minus 2, 4 minus 1, 4 raised to 0, 4 raised to 1, 4 raised to 2, like this. And see, this H is subgroup of G because 2 is not there, and it is obviously, we can say it is a subgroup. And what is the definition of subgroup? Subgroup is group itself. This become identity. 0 power of any number is identity, and inverse of 4 is this. Inverse of this element is here. That means this becomes subgroup. And why it is subgroup? Because the element 2 not belong to H. H is subgroup since 2 not belong to H. Therefore, you can say H is subset of G. H is non-empty subset of G and H itself a group, that means H is subgroup. This is by definition. Now we claim this and we prove that this is subgroup. Right? Come now. First thing, to prove this equal to this, we prove, first part, we prove AM contained in H. AM contained in H. This is anyway obvious result because we have supposed AM belong to H. That means H is subgroup. So by closure property, we can say this is why we can say this has element of this type, and that means in expanded form, this means this expanded form I write like this: A minus 2m, A minus m, A 0, AM, A 2m, so on. Now you can see this is subgroup and contained in H because H is this. So obviously since H is given subgroup, then by closure property, because any element we take and we take product of them, then it will found in H because H is subgroup. So AM contained in H. Second part. Now second, we show H is contained in AM. Now we show this part, right? To show this part, we suppose some element B of H and we find or we decide that element also be there. So let B belong to H implies B belong to G because H is subgroup of G. So B is what type of, because G is given cyclic, therefore B is expressible in terms of A, implies B is equal to AK because G has all element of the type some power of A. Now we show that AK, now we show AK belong to AM. Now by division algorithm, by division algorithm, algorithm K is equal to MQ plus R, where R either 0 or between 0 and M. This is by division algorithm. Now taking base A, we have AK is equal to AMQ AR, and from this I can write AR is equal to AK into minus MQ. Now what happened? This MQ is element in this set, because this set has negative and positive numbers. Therefore, now this product. So what actually we get? We have to show somehow that R is equal to 0. So how we can show this? So we show that this is, we say that this element belong to H. Why? This is the question. Because see, AK, that was B, we chose from H, and A minus MQ also belong to H. Why this belong to H? Because already we have shown AM contained in H. So H is the bigger set, that means this element also be in H, right? Now this implies AR belong to H, and we say R is 0. Why we say? We say R is 0. Why? This is the question. Because our position was M is the least positive integer, because our position was AM belong to H and M is least positive integer. But R is smaller than M. Therefore, if R is smaller than M, therefore, what possibility we have for R? Therefore, R is 0. R is 0. This means if in this equation I put, then what I get? I get so AK is equal to AMQ. Here putting R0, then I get this. This mean what? AK belong to AM, that means AK is expressible as some power of AM. This give us what? AK was AK was B. This means, but AK was B and hence B belong to AM implies B was element we chose from H. That means H is subset of AM. Now, in the first part we showed that AM is subset of H, and here we showed H is subset of AM. This means H is equal to AM. H is equal to AM. Hence, H is cyclic. Hence, H is cyclic. So, this is the technique